Hi, I'm whispering because this next effect I'm gonna teach is noise activated. Here, let me show you. Kamehameha! I still have to whisper because otherwise this thing will start over again. Anyway, I've just reached 2,000 subscribers and I thought I'd do something special and go back to my Dragon Ball programmatic effects series I started over 2 years ago and teach you how to do this thing using only a webcam, microphone, these wristbands, and vanilla JavaScript and HTML canvas. There are no libraries whatsoever in this, so that you really understand what's going on. And if you're new to the channel, you may want to watch this video to learn what this whole thing is all about. And if you're curious to know how I'm motivated to do things like this, check this video out. And I'm filming in... Oh! Alright, watch the whole video to know where the source code is and what I'm planning for this series next. Skip to the intro. Gonna code, debug and have fun. Coding with Radu. Coding with Radu. Gonna prototype and design. Coding with Radu. Coding with Radu. Let's code now. We begin with basic HTML. In the head, I'll just add the title for the page. And in the body, I'm going to add a canvas element. This is going to be a canvas app. Okay. Now, if you refresh the page at the moment, it doesn't look like anything because the canvas is transparent there. And you can see that it is there, and the body also has a little bit of margin on the side. We are now going to go to our HTML file and include a CSS file to do the styles. So in this CSS file, I'm going to add a dark background to the body and remove this margin. And the canvas element, I'm going to make it visible by giving it a white border, like this. And let's put it in the center, so absolute positioning, 50% from the top, 50% from the left, and transform, translate, -50%, -50%. This gets it in the center of the screen. And I want the canvas to stretch the whole size of the screen. So maybe not 100% width, but 98% width, so that in this way you can still see the side margins, the side border. Otherwise it will be glued to the side of the browser and not very visible. So now if I refresh, it looks like this. So the canvas is there, it's stretching horizontally, and vertically we'll get to that. But now let's go to our HTML file and start to write some JavaScript code. I will write a little bit of JavaScript here, even though it's quite common to do this in a separate file, because here I just want to initialize our effect. And the effect will be written in the other files, but here I just want to access the camera and microphone, which we need for this one. So I will ask the media devices of the navigator object to get user media, and I will ask for video and audio this time. Usually my tutorials will only include the video part, but this one is different here. And when this promise resolves here, so we have a callback function that we pass to this then method. In this callback function, we have access to the raw data coming from the camera and the microphone, sending this raw data as a function argument there. So here inside this, we can use the raw data somehow, which is video and audio this time. And what I'm going to do is I'm going to create a video element and pass this data to this video element like this. And now I'm going to play. But usually we don't need to do this in my other tutorials, but now because this one includes also the audio part, we should set here the volume to 0, because otherwise we will hear ourselves back as we speak in the microphone. So we will get this weird loop back effect without this setting volume to 0 here. And now I'm going to listen to this unloaded data event, because when we get video from the camera, it might take a few milliseconds for it to initialize. And in this way, we prevent any future errors popping up. So we will only use the video element after it has gotten the data. And when it's there, we have a callback function here, and we can, for example, put our canvas element, this my canvas element from the HTML DOM. We set its width and height to the video width and height coming from our camera. So these values might be different depending on what type of camera you have, but anyway, it should work. And to test, I'm going to try to put this video image on the canvas context. So I'm getting the context of the canvas and use it to draw the video on the canvas like this. So I start drawing the video at 0, 0, which is the top left corner of the screen, and I fill the canvas with the canvas width and height. And if you look here, the video width and height is the same. So I'm essentially filling the canvas with the video coming from my webcam over there. And this is just to test. We will be deleting this code soon, but it's good to write here a catch, because it's possible that the user testing this application is not going to allow the use of camera and microphone, or maybe the device doesn't even have a camera or microphone, so it should give some kind of error to the person using this application. And now let's refresh, and you can see now this static image of me looking in the webcam there. So it seems to be working. So basically I have this way of accessing the video. I haven't checked the audio yet. We will do that a bit later. But now let's include these JavaScript files that we will be working with next. So the whole effect is going to be processed in this kamehameha.js file. And we will also need a utils file, because this code will be relatively big. So I'm going to separate some functionality in this utilities file that can be useful to other projects as well. And finally, I'm also going to include the visual effects of the Kamehameha. Now, this file is actually already written, but you don't have to worry about that because I do have tutorials on how this code works. So check those out if you're interested. Otherwise, you can just take this code from my website and use it in one of your projects. But basically, this code is already written, and what I'm going to teach you today is how to apply the visual effects to our gestures when we move in front of the camera and when we talk into the microphone. So I will still explain how this code works in this video, but I won't write it because it's really a lot of things to do there. So let me remove now this code here that is used for testing and initialize here our Kamehameha effect using the canvas and the video object that we just created. So I think that we are pretty much done with this HTML file here. And now we can move in our Kamehameha.js file and implement this Kamehameha effect class. So in this file, I'm going to define a class, and the constructor is going to get the canvas and the video object, and I'm going to set these as attributes inside of the Kamehameha object, like so. And I'm also going to put here a context that is handy, because the context is used to draw all the elements on the screen, and we don't want to refer to it every time. And I'm also going to call here an animate method. This method is going to draw initially on the canvas our video. So this code is very similar as what we had previously, but now we need to use here this, because the attributes here are stored inside of the object there. But what this does at the moment is pretty much what we had for testing in the HTML file previously. The difference is that here I'm going to call request animation frame. So what this is doing, it's going to call this animate function again and again on every frame. It will try to do 60 frames per second, but depending on your processor, it might work a little bit slower than that. I think this effect is actually not very processor intensive, so it should be just fine. Now there's a problem, because if we call animate inside request animation frame, animate forgets what this is here. It will be referring to the scope of the request animation frame function there. So we still want it to mean this object right here that has the canvas, video, context, these elements that we are using. So we need to bind here this and essentially tell the animate method what this means. So now when we have also request animation frame in place, if I refresh, I'm getting a live image feed there. And let's see if we can do this video without the bottom video of me talking. So I'm just gonna focus on this camera that I'm using to debug at the same time as developing this effect. Let's see. But anyway, now let's continue to write this code, and what we need to do next is figure out the location of the blue elements in the screen. So in my intro you saw that I'm using those wrist bands because they are part of the series, and essentially they are the marker that we don't need another marker like this one, like I'm using in my other videos. They are the marker for this effect, and it's great because they are needed in the costume if you're gonna be cosplaying or something like that. So basically it's perfect. Now in this tutorial I will still use this marker for convenience. I don't want to get up and do the pose every time I'm refreshing and debugging here. So consider these as the two wristbands, this cap right here and this one right here. They are a bit different size, but it won't matter. You will get the idea of how we are going to generate this effect using this one. So we want to find out these marked locations, these pixels that are blue somehow. And I'm going to write here a call to this getMarkedLocations function from this canvas context. So this function is something we need to write now. And when we get those locations, let's just write them here as so. So this getMarkedLocations, the locations that are blue, we want to know the XY coordinates of each blue pixel here. This is a utility function. This is something I've been coding in many of my videos. So I'm going to move to utils.js. and right here get marked locations like this. And the locations array is going to be empty for start, but then we are going to get the image data from the canvas context, and I'm going to get the whole image data. So starting at the top left corner of 0, 0 and ending at canvas width and canvas height right here. And let's just log this image data here for testing purposes, see how it looks like. And I refresh now. And you can see here image data being logged in the console. The image from my camera has 480 height and 640 width, but the important part here is this data attribute of over 1 million elements. So this is 480 times 640 times 4, because inside this data we have all the pixels written one by one, starting at the top left corner and then going to the right and to the bottom, with RGB alpha for each group of 4 components. So let's actually focus on the top left corner pixel here. And print this one. So now I'm printing just essentially this top left corner pixel to see its value. So we have there about same kind of values, about 150 for each. But if I'm gonna put here a blue marker, you can see these values are changing slightly. I'm gonna try to match those values there. So let me just go here and define the color that we are looking for. So it's something like this, 10 for red, 100 for green, and 210 for blue. It might be different in your case because lighting matters and maybe your marker has a different color to it. And you could see that the values are really changing all the time. So this doesn't need to be perfect. And because this doesn't need to be perfect, we're gonna use also a threshold here. I'm gonna just set it to 60. We'll see what this means soon. Just bear with me for the moment. Essentially, I'm going to allow different shades of blue using this threshold value. So let me just go down here and go through all the data elements. So that long array, I'm going to increase I by 4 here at each step, because I'm essentially going to go pixel by pixel. So in those groups of 4, I'm going to jump pixel by pixel and get the red value of the pixel, and then the green value of the pixel, and then the blue value of the pixel. And the fourth component would be this alpha value of the pixel. But we don't need this. There are all 255 because cameras don't have transparency support, at least not regular ones. So now what we are going to try to do is have a match between our RGB value of each pixel and the color that we are looking for at the top under a given threshold. So if there is a match under a threshold, then we are going to get the index of the pixel first. So this is just I divided by 4 because we're jumping in groups of 4 with I. This will be an integer value, so we don't need to floor this or round it in any way. And now to really understand a little bit how these go, I'm going to actually go here and pixelate my image. So I'm pixelating my image just to prove a point, because otherwise you can't see the very small pixel values. So now P index is going to be 0 for this top left corner value, and as we go to the right, this increases. So this image has a width of 32 pixels, but the original one from my webcam has 640, I think. So it doesn't matter, we will use the width value as it's coming from the camera. But I want you to see that p-index increases to the full width, in this case 32 minus 1, because we're starting the count at 0. But then as we go to the next row, this p-index actually just increases even more until the next time, and so on. This is an array, it's not a matrix. So now the question is, what is the xy coordinate of this? So we want the y to be 0, 1, 2, 3, 4, 5. And we get 5 by dividing 167 by the width of this image. So if you divide that by 32, which you know already, you're gonna get 5 and something. So you take just the floor value of that to keep the integer part. And then for this part on the left here, you want to get 0, 1, 2, 3, 4, 5, 6, 7. That's actually the remainder when you divide this by the same width, 32 in this example. So essentially, what we are going to do now is get these y by getting the floor of p-index divided by the width, whatever that is. Remember, the canvas has the same width as the actual video coming from the camera. And then x is going to be the remainder when we are considering the same width. So that's how we get x and y. And I'm just going to add these x and y values to this locations array that we defined here in the beginning. So we are getting these groups of xy values there. I mean pairs. Okay, and now we just return these locations, but we are not done, because this color match function here is something that we need to define. So how do we match colors under a certain threshold? And for that, I'm going to show you this 3D view of colors. So colors can be actually seen as points in 3D space. If you increase the amount of red, of course that means that the color becomes red, but it also can mean that on a 3D space, our point is close to the far end side of this axis. And if you add green to that, then it's gonna move your point also upwards on this axis. But it also means, of course, that the color is gonna be yellow this time. And we are looking for a specific color value here for this 10, 100, 200, and 210 here. So let's try to see how that looks like. I'm gonna put here a value of 10, and then green was about 100, I think, and blue was much more. We are looking for blue, but you see that it's not pure blue. It's always some kind of mix. It's rare that you get the pure color from the camera sensors. So this is kind of how my marker looks like. But we want to have a threshold here. So we want to tolerate more colors. For example, if you have a color here, is this close enough or not? And our threshold here is 60. So what it actually means is that if you consider a radius of 60, if that other color that we encountered there is going to be I can't do it exactly, but you get the point. So if that color is going to be inside this sphere, then what it means is that we are going to consider this a match. So that's it pretty much. We just have to calculate the distance between our given color and this RGB color of every pixel. And if the distance is less than the radius of threshold, then we have a match. So what we're gonna do is go back here, and the distance below a threshold, this is a true case, so we can put here return and just get that value. If it's above the threshold, then that comparison will be false, so we don't need an if statement here. All right, so we need the distance function, and the distance function is something I've implemented very many times, but it's basically the Euclidean distance. In this case in 3D space, but I usually like to write it like this, going to the length of the point. So if you have 2 dimensions or 3 dimensions or any number of dimensions, really, you can have high dimensional space, this function is going to work. And in 3D, well, in 2D, you just get the hypotenuse of a triangle. So basically this is using the Pythagorean theorem. In 3D, this is using the Pythagorean theorem twice, actually, to get the length of the diagonal of a cuboid. And in 4D, you can go, yeah, I'm thinking about making a nice video about the Euclidean distance. And if you're curious about the Pythagorean theorem, I have a good video about that one as well, so do check it out. So yeah, the formula here is quite easy. It's just the square root of a sum of the squared differences on x, y, z, whatever the dimensions are. Here I'm just counting them as 0, 1, 2, and in that way I can have as many dimensions as I want without running out of letters. So that's going to be our distance function, and I think we are pretty much done. Let's see. I'm going to refresh this, and look at that. Our marked locations there, it's empty, but as I'm adding here the marker in the screen, it gets many values in it. Let's see if I move this marker really quickly, does it? Not all the time, but sometimes. So maybe this is not the best way to detect if maybe Sonic passes by, but I think it can be a good burglar alarm for some other blue character. So we basically can figure out now if there is anything blue in the image, and I think that's great. But I don't like debugging just like this. I usually like to debug things in a very visual way. So if we have locations, I'm going to go through all of these locations here, and I'm going to actually show them on the canvas. So instead of using a console log there, I'm going to use a white color, and I'm going to draw a rectangle at each location, so x and y value, and with the width of 1 and the height of 1. This is basically a very small rectangle there that I'm going to color, fill in individual pixels. And now if I refresh, I'm gonna get here the blue values. This looks quite nice, colored in as white, because you see we are essentially getting all the locations, all the x and y values, and now we're just drawing white rectangles on top of these. So much better, and you can see now if I move very quickly, then this is so blurry that it doesn't have time to register. I mean, the threshold is probably too little, and the blue is not really blue, it's like this faded gray or something. But immediately when you switch directions, you get it. So if your camera has a high frame per second, a high FPS, then you can use this even better. But now you have to kind of consider that you can't be moving extremely fast. you can move pretty fast, but not like Sonic. So now that we have these white locations, the next part of our algorithm will be to get the average value of these. And let me just go here and set that we want the point C to be the average of these locations. And I'm going to go into our utility file here, and I'm going to define a function. So I named that C for center. So this is average is just going to be the center of mass of all these locations. And I'm going to go through all of them and add each x and y values for starters, or 0 and 1 values, because I like this notation better. And then I'm going to divide by how many locations there are. So essentially I'm calculating the average of the x values and the average of the y values like this. And I return this center point, where 0 is x and 1 is y. And here inside of our animate method, I'm now going to just show this point as a light blue color circle. So I use this arc method, and here I'm deconstructing this point. So one good thing about writing points as 0, 1, like arrays instead of xy objects, is that you can deconstruct them using this syntax, and I don't need to write C of 0 and C of 1 there every time. So it's nice. Then the radius is going to be, let's just have 30 for now, and we have to write here 0 and 2 pi because we want to draw a full circle. And we are going to fill this value with the light blue color. And let me refresh. And now you see an average location of these. And it's kind of normal for it to be closer to the top part, because that has more blue than the bottom part. Maybe unless I do this. So now this bottom part of the marker is closer to the screen, so it has a bit more blue pixels. And now this C point is kind of in between. But this is actually a bit of a problem, because when you're doing this like with your wristbands or whatever, it's possible that even though they might have the same size, to the computer they might not. Like if a shadow is over one of them, then maybe you recognize more pixels in these marked locations on the top one than on the bottom, which is usually under shadow or something like that. So we need to do something about this. This is not where we want our energy wave to be. So what I'm going to do next is try to find actually these endpoints. So where is this one wristband and where is this other wristband in this case? I want to find these somehow. So what I'm going to do first is find this marked location that is the furthest away from this big circle right here. So something at the bottom of this marker. And I'm going to do that. Let's name this point A. And say get furthest from. So the furthest of the locations, of the white locations, from C. And this is a utility function. This can come in quite useful in other projects as well. I think I've used it before also. So what we are doing essentially is getting a maximum distance point from these locations. So I will initially consider that the first point, so locations of 0, is the maximum distance, and I will choose it as the furthest away point. But then I'm going to loop through all others. So I start here at 1 with I, and loop through all other locations and calculate the distance at each step. So if our new distance is greater than the max distance that we had earlier, we update that max distance and the furthest point to be the ith location instead. And this is pretty much standard. We just return now this. Getting a bit tired. So this farthest point here, and that's it. Notice that we're using the same distance function as we had previously for the 3D color space. So these are just 2D points here, but because we wrote it like that using a for loop, it's really useful at this stage. So now with this location there, I'm just going to draw this A point to see how it looks like. So let's get this, let's give it a red color. I'll put a smaller radius here. And fill it, refresh the page. So now you see this A point, this red point here, it's the bottom wristband, if you will. And the C average is still here. But what we want to do next is also get the other wristband. So we are going to now find the furthest away point from this red point at the bottom. So let's reuse this function here. So get the furthest point from A this time. And now, okay, let me just copy these. I think it's fastest like so. So A here is going to be B. I'm going to draw also the B point. And I keep that one red also. So now we have both wristbands there, or both sides of the marker, and this C point that we actually would like to be in the middle of these two wristbands. So the logic here is that you will likely get at least some blue values in those wristbands, but maybe they are not going to balance out how many there are because of shadows and your posture and things like that. But the average location of this red and other red point is going to be in the middle. So what I'm going to do next is pretty much have C update its value. So we don't need the previous value anymore. I just want to take the average of A and B, and our average function accepts an array here. So I'm going to create an array with our A and B arrays for points. A and B have 0 and 1 for X and Y there. So now with this one, maybe we can paint C here instead. Let's refresh. And now C is better. C is in the middle of the two wristbands, no matter if one wristband is a little bit bigger than the other, maybe not tied well enough, or if there's some shadow in them, we have now the point in the middle. Great. I don't think I need all this other stuff anymore. Let me just... Okay, let me actually have here a little bit of a cleaning up step. So I'm moving all the logic in this place here. I don't need to draw these white pixels anymore. They're actually slowing down your processor quite much, and it's something we don't need. We don't need any of these. These are just debugging things for now. So let's try refresh now, and I think my computer is going to start to not do so many, not use the fan so much. So at this stage, we have the center point and A and B. A and B are also useful to define this radius. So here I have a radius of 30 in this case. That's just an arbitrary value. What you want to do is actually get a value for this radius. Like radius can be the distance between A and B. If we divide this by 2, then this is gonna connect A and B directly. So if I'm gonna refresh this now, oh, I'm not using the radius anywhere. So if I'm gonna paste here the radius instead of this 30 value, now our circle is pretty much gonna match those, but you don't want that. It's too much, because the wristbands, like if you think about this pose, one is here and the other one is somewhere here, so maybe 30% of this distance. Let's see. And I'm actually going to use another marker to simulate the wristbands. I think it's a good idea. So, okay, hard to figure out where it is, but I think this is kind of like what the position is like. And yeah, I think this 30% value is pretty good. So considering that those might be the wristbands there, I have now this I have now this energy ball here. This is kind of fun. I'm getting so many ideas with these markers. It's such a simple concept, but you can do so many fun things with them. I'm gonna do many videos with this if I have the time. What do you think? Do you want to see more tricks using the markers? Comment below if you want to see more of these videos. So, okay. Let's stop debugging now and move on to the visual effects. So I'm just going to include the code that I did in my previous tutorials. Let me... yeah, we don't need this at all anymore. So logic is actually very simple. All of that was just to debug and make sure that we don't have any errors. And here what I'm going to do is refer to our visual effects. So I'm going to have VFX attribute here on object equal to new VFX. So this, oh okay, it's all caps here, I forgot. So this code has been already explained in my other tutorials. I did change a little bit from there. I made it use a class syntax, and also I updated a bit modern JavaScript, so the vars are now consts and these are methods, they are not functions, but all the logic is actually the same as in those videos. Plus you can get the code of this, what I'm doing today, including this, from my webpage. So there will be a link to that in the description, or maybe I'll pin a comment or something like that. But basically you can get this if you want to play with it. And after we initialize this, we want to draw it on a context at a point with the given size. So pretty much here all we need to do is say this VFX draw on this context. The point is at C, and the given size is this radius value. So I'm going to save this and refresh. And now if I add this here, this looks awesome. I like this. I made it model the Kamehameha that Goku did in the tournament against Piccolo. So it looks cartoonish. Of course you could make this look more realistic if you really want, but I went for the cartoonish variant in this effect because I think it's great. I really liked it, and it's very geometric. So I'm gonna teach you next how this effect was made, even if you don't watch those videos with those tutorials for how the code works. I'm gonna go through it quickly now. Well, I don't know how quickly, but yeah. So in this code you see there are two states. This is the first state, the ball, and then we'll also get the wave. We'll see that a bit later. But this is made of three different methods. So this glowing ball, rays, and electricity. So let's look at them one by one. And I'm going to look at the glowing ball first. And I'm going to save this, refresh, and now when I show this, it just has the glowing ball component. So this code is actually more complicated than you would think, because what I'm doing here is I'm defining a polygon that is essentially a circle right here. So I'm just going from 0 to 2 pi radians or 360 degrees, and I say add some points there with a small step. So I'm making a polygon with so many sides that it kind of looks like a circle. And then I'm drawing a glowing polygon using this method here. Now, I know you're probably thinking I can do the same effect with gradients instead. Just don't go through all this trouble. But you'll see later why I do it this way. I promise it will make sense. Now, this draw glowing polygon, it actually draws this glowing polygon. The fill is just white, so there is no nothing strange there. It's just the white values from here, so 250 to 50 to 50. But the stroke is actually a collection of many strokes, starting at this blue and going through this transparent white. So we have here an interpolation method here where we interpolate between these two colors. Watch the tutorials for it to make more sense if you're interested. But basically I'm drawing the glow right here as many lines that are overlapping each other, starting with the very transparent thick line, and then as the lines get shorter they become more bluish in color. And that's one way of drawing gradients that is overly complicated for the circle, but you'll see later why I do it this way. So this was the glowing ball part. Let's comment this out and draw the rays. So the rays are these things. So these things, they are not very complicated. The glowing ball is more complicated than this. The rays is essentially doing the same thing as previously, so going through a circle. So again, a small step, it kind of looks like a circle. Let me actually comment out this angle offset and set it to 0, because the non-spinning rays are much easier to explain. So you just go in this circle and you say use a radius of 0, but sometimes when your point index, so which point of the circle you're drawing, if it's going to be a multiple of 8 or a multiple of 8 plus 1, then use a radius that is big, like the maximum of the width and height of the canvas times 2 apparently. And then draw this polygon. So you have a small circle in the middle which is like 0 radius, this one, but sometimes it jumps to a big radius, the size of the screen pretty much, a bit more than that. So you have small radius, big radius for just 2 points, and then back in the center small and then big. Every 8 points these things happen. And then you actually use the radial gradient method here. So radial gradient from white that is fully opaque to fully transparent at the at this maximum of the canvas width and height value. So that's why these rays begin to fade as they are approaching the side of the screen. And yeah, and this angle offset is something that I'm adding here to the circle, so that this value actually depends on the frame count. So the frame is increasing by 1, it starts at 0 when we initialize this effect, and every time we draw it, our effect increases in the frame count. So I can draw these rays animated by offsetting the angle using this frame divided by some value here. So I couldn't find good names for all these methods, but offsetting gives you this rotation of the rays there. Now, what might be the most complicated part of the code here is actually this electricity. I think you can do it in many ways. This is just my way of doing it here. So this electricity here is actually, well, you can see something happens around the circle. What happens is actually that you generate points. So you're going to generate random points on each frame. So you have here a value on the circle, so starting at a radius of a given size plus an additional random increase. So you have the circle expanding to the size, and then it expands randomly to some value. So you're going to get points that are randomly distributed around the circle with some extra margin here. And then for these points, we don't draw these points, but we do draw links between them. So we draw links between from one point to the nearest two other points. This doesn't mean we get a fully connected graph. Sometimes we get these gaps in the middle, and I think that's just how it needs to look like. So here we get these two nearest neighbor links. We just go through the nodes and get the k nearest neighbors. In this case, k is equal to 2. And the get nearest neighbors, it's pretty much calculating the distance from each point to all other ones and sorting the array so that the only the first two smallest values are obtained. So I don't sort everything. This is, I think, selection sort. Yeah. And I only sort up to the first k, so I'm not doing quadratic time complexity here. And I'm returning these neighbors. And for each of them, I just, for all of these links, like the two nearest connections, I'm just drawing lines there. And it kind of looks like this kind of static electricity effect. So, putting all of these together, we get this. But now let's move on to the sound processing part, and then I'll explain this wave code a bit later when we get to that. So, we don't want this ball to show in the beginning. We can do that, for example, by setting here the default state to maybe be idle. So what happens now is that if we refresh this and show it, it's just not going to display because it doesn't match the ball or the wave, like this. So going back here, what I'm gonna do here is figure out the volume of what the microphone is receiving, and if the volume exceeds a certain threshold, then we set the state to ball. So simple enough, maybe, I don't know. Let's see. So what I'm gonna do here is get an instance of this audio context. So we are gonna use the Web Audio API for this, which is native in JavaScript. And we are gonna get I'm gonna define here a variable called microphone, and I define this by getting create media stream source to the source object of the video. So essentially that raw data that comes from the camera, it does have also the audio component, and I'm taking the stream from that into this microphone object there. Now we will need to analyze this object, so I'm going to call here create analyzer from the audio context methods there, and I'm going to connect this microphone to this analyzer like this. Okay, so now that we have this in place, we're gonna move down here and let me just log what the volume is. So in each animation frame, we check to see what the volume is. And if the volume will be greater than some value, then we will set the state to ball for our visual effect. But now this, how to say, this get volume function doesn't exist. So it's something that we actually need to define ourselves and implement ourselves. So we need to understand a little bit about how the signal works. Like, what is this raw data, raw audio data that comes from the webcam? So what I'm gonna do is go here and say get volume. This is gonna be a method that takes that is gonna get a data array from our audio context. So first we need to define this data array using, I'm gonna use here an array of float values. So this is how you do that. And I'm gonna set the number of elements to this array to something called the frequency bin count. Now this will become clearer soon. I'm gonna visualize this as well. But this data array is now empty, and what populates it with the value from the analyzer is this function. I'm gonna use this get float time domain data. So this one will get the data from my microphone as a float array and pass it inside this data array right here. And now I'm going to log this into the console, and I think we can test. So let's see how this looks like. Something doesn't work here. Oh yeah, this only works when we have some blue locations on screen. So let's move this here. And now you see some values there, some very small values like -0 something, +0 something. So the volume is only used when those colors are on, when the color is on screen. And now I'm just printing it there, but I'm not gonna attempt to explain it like that. Instead, I'm gonna visualize this. So what I'm gonna do here is essentially remove that line and start to draw on the context what these numbers look like. So I'm gonna draw a horizontal line that spans from the left part of the canvas to the right part of the canvas, and that will mean the full size of this array. So this data array that comes as the data from the microphone. So I'm going to begin drawing a yellow line so that I see it somehow, because my background is kind of whitish here. I'm not going to use that. And let's move to half the height of the canvas. So I'm going to draw it starting here in this point. And the line will just go like this all the way until here, but vertically I'm going to plot these values in the data array. So we are going to get a waveform. And let's do this by going through all the elements in the data array like this, and do a line to the width is going to be depending on this I value. So when this I is going to be maximum all the way to data array length, then this value here will be a 1, and then we're approaching the width of the canvas, so all the way there. But in the middle we will interpolate the values, so all possible values depending on how many items in this data array are there. And let's have here also the height. So relative to this midpoint in the middle of the canvas here, we're going to go up and down depending on these values you see in the console here. So some are negative, some are positive, but around 0, between -1 and 1, I think. So let me just go back here and say, depending on the value at the ith position of this data array, multiplied by some value. I'm going to put 100 here. Yeah, because if not, then a 0 value or around 0, it's not going to look like anything. So let me just do this. And yeah, and I need to stroke. And I think I can refresh now, and if blue is not on the screen, so with blue on the screen, we can see there a waveform. So this corresponds to whatever the microphone is receiving there, but it's like a time window. So it's a time window, a very short time window, a few milliseconds probably, with different values and how the vibration changes. So if you don't know how speakers work, if you look closely at the speaker, you're going to see it vibrating a lot. So those small vibrations happen many, many times per second, and they produce high pressure waves and low pressure waves in the atmosphere, in the air around you. So that's what these values mean, that a speaker goes up or down, like inflates or deflates. I'm not sure what the terminology is here. But basically, this time window here is small, but it does show how this speaker changes. And microphone is just like a speaker, it's just inverted. So a speaker takes this kind of signal that you see here and makes it into vibration. But the microphone vibrates because I'm making these pressure waves in the atmosphere, and they are going in the sensor and they are collapsing it or pulling on it, and it transfers them into this binary digital signal form. So basically what we see there is how much I compress or decompress this small sensor in the microphone. And to get the volume for this, there are many ways to do it. I'm just going to do a very simple thing now and take the maximum value of this. So you can kind of see a periodical nature of this. It's like a wave, and it goes multiple times to maximum and multiple times to minimum, like negative value. I'm just going to focus on the maximum value and just report that. So if I'm talking like this, it's going to be lower. But if I'm going to talk louder like this, then the maximum is going to be louder. So let me just return here the maximum value of this data array as the volume. And the maximum function here actually accepts any number of arguments. So I'm destructuring this array here, and I can just use it like that. It's quite convenient. Okay, so let me refresh. Okay, and now when blue is on the screen, you see a number there in the console. And if I'm talking not so loud, then these values are maybe below 0.3, 0.4. But if I'm talking louder, then those values go higher. So what we can do here is say, if this get volume is greater than, let's say, 0.4, then I don't need this anymore. We can say this VFX state is equal to ball. And now if I go here and refresh the page, and okay, maybe it's a bit too low value, so let's put 0.5 here instead. Now if I'm gonna talk not so loud, nothing happens, but if I talk loud enough, then the effect happens. So that's what was happening in the beginning. I was not reaching this kind of threshold there, and yeah, but I don't think I need this yellow line anymore, so let me just remove all this, because it doesn't make sense to have this in the get volume. This is just displaying sound. I'm visualizing sound. That's so great. So now, ha! Now this works, and it's great, I think. So it starts in this way, in this ball shape, but now I want it to turn into the wave shape when it's moved significantly much to one side. I think I'm gonna cover this bottom part of the marker there because it's clear like this, so I'm gonna try to remember to hold it like this. So now what we want to do, if it's in the ball state, I want it to switch to the waveform when it's moved really quickly to one direction. So let's try to code this in. So here we actually set it to ball if the volume is greater than that and this VFX state is equal to idle. Otherwise, when we are in the wave state, it might switch back to ball again, and that's not what we want. So here we say if this VFX state is equal to ball this time, now we're going to try to figure out the conversion from ball to wave. So I want to do this VFX state is equal to wave if something happens. So to detect change in location, we're going to need the previous value of C somewhere. I'm going to just put it here as old C is equal to, let's just give it the value of 0, 0. And every time we are getting a value of C here, actually after we are done with this, we can say this old C is equal to C. So we are updating the value of old C. And now if the distance between C and old C is greater than some value, like if it's a significant movement, then we switch it to wave. What this value is, it's not trivial to figure out, but we could use the corners of the screen. So this length of the diagonal, this is the furthest movement that we can do physically. So we could get that value by doing math.hypot. If you didn't know, you can get the hypotenuse of a triangle in this way. So hypot between this canvas width and this canvas height, like so. But we cannot get this value, like we can't get the distance that is bigger than this value, so we just take a fraction of that, maybe 0.2 of that. So if this whole diagonal is the 100%, 0.2 is probably gonna be something like this. So if it moves this much, I think it's gonna be enough. So we don't want to have accidental triggerings of this. So we want a significant amount of value. So if this distance is bigger than that, then we have here the state changing into wave. Okay, now let's see. Okay, alt C is not defined. I forget here this alt C, and ha! Okay, so if I move it not so much, nothing happens, but if I move it fast, hey, it worked. So now it has the wave state, and yeah, and of course because we have here this radius defining all the time, like our code here, then this is going to change size depending on how far you're hands are from the screen and things like that. So I think it's a really nice implementation, and it works pretty reliably. You can use this to make a real visual effect just by playing around in the webcam, in front of the webcam, and recording the screen. So we need to set this back to ball after the wave terminates. So this is the final thing I show you now. So if we are changing this to a wave, let's put the timeout. So set timeout function, and I'm gonna say that after 3 seconds, so 300 milliseconds, put the state of this back to idle, like this. So not double equals there. So like this. Ha! And now, pew. Oh. This is no longer working because now we're inside this function from here, so this means something else. But a trick in JavaScript is that if you use arrow function notation like this, this is no longer changing, so the code should work now. Sorry, I'm rushing things now, but I actually have to go somewhere in about 20 minutes. Ka! Okay, so in the final version of the code, I'm also gonna put there some kind of a bit better effect, maybe. Okay, I'm talking loud enough. Maybe I'm gonna do a little bit of a fade in the beginning and at the end, or something like that. And definitely I'm gonna put in the sound effects. So I generated the sound effects for this also programmatically, and that was probably the most difficult part of this whole thing. So I haven't made a tutorial on that yet. Let me know in the comments if I should. I think I will eventually, but I don't know how soon. It's challenging, but I think I can teach it well enough. So, all right. Now, before I go, I have to tell you also how this wave is implemented. And let's go here in the VFX and check this wave function. So I'm going to comment out everything except this draw wave path. And now, ka. So what it is just a rectangle, but it has these borders. So it has the same borders as the this kind of glow effect as the ball had previously. And now you can see why I did that kind of function that draws a glowing polygon previously, because now I just give it A, B, C, D corners of this rectangle that I want to draw, and yeah, and I can use the same function, this draw glowing polygon, to give glow to that. Otherwise, it's very difficult to make a gradient like that. It's actually impossible using the built-in methods. So that's pretty much what this part is. This second part, the wave source, so the source where the wave is coming from, which looks like this, it's actually made of two different circles, circular kind of shapes. So I changed here the circle, I squish it a little bit. Do watch the tutorial if you want to know exactly what these functions do. And I think I can demonstrate something without this randomness added to it. So, ka. Now you see it's not doing those kind of random movements anymore. So basically it has two shapes, kind of like elongated circles, and it's not drawing them individually, but it's jumping from one to the other depending on if this point index is odd or even. And of course I'm using the glowing polygon to draw this shape as well. Let me add here the randomness again. And the last part here is actually very easy. It's a masking, I'm calling it a masking rectangle because it's just a white rectangle that I'm drawing over everything else. If I don't put this here, then what happens is that it's going to show this kind of blue lines of the wave source that are over the wave path. And I don't think that makes sense because it kind of implies that the source doesn't continue into the path. So here, these blue lines that you see above my finger here, I'm hiding them using this another white rectangle with some with no blue in it. With no blue in it this time, I'm hiding it a little bit. So that's it. And these are actually also using direction. I forgot to do this. So I'm only testing what happens when I'm moving this way, like that. But now if I'm moving it this other way, it should go opposite direction. So final thing that I'm doing before I have to go. So when we are deciding that we're going to use the wave, if this old c of 0, so the x value, if the x value of the old c is greater than c is x value, then what I'm going to do is VFX direction is equal to math.pi. So flipping it by 180 degrees. Otherwise, this VFX direction has to be 0. And I need to do this else here because I can now do the effect multiple times in the same page refresh. So I don't want it to get stuck in the pi. Okay, so that one worked. And other direction works. Great, great when everything works. So yeah, that's it, I think, for today. Do check out the source code on my website, and it will be a little bit different because I think I will polish this a bit more before I release it, but I'm not worried. I'm sure that you're gonna understand what I'm doing there. Just a little bit polishing things, like maybe fading it in and out, and yeah, those sound effects. So the sound effects, hard stuff, I haven't made tutorial on that yet. It's synthesized, so it's procedurally generated sound using the Web Audio API, and it took me the longest time to get right. So I am planning to make a tutorial on that, explaining how this sound can be generated just using code, but I'm not sure when. So let me know in the comments, do you want to see tutorials on procedurally generated sounds? I've done these sounds also for other videos, like the Spider-Man, web shooting, and I also have something with lightsabers, but I'm not sure if I published this before or after that. So, spoiler alert, there might be a video of lightsabers if I haven't published one yet. So anyway, if you want to see how I'm making the sounds for those, just using code, do comment below. And yeah, so I really like this topic of Dragon Ball, procedurally generated visual effects, and other kind of visual effects, not just Dragon Ball, other anime or other things like Spider-Man from the Marvel Cinematic Universe nowadays. I mean, as always. But Yeah, so I really want to do many things. I kind of have this idea of having a page where you can just go in front of the webcam and do different attacks when you want them to do. Because anime has these things that you shout out the attack for, I don't know, the opponent to know what you're doing or something. I don't know. It can be very interesting to detect what attack you're doing based on the thing that you're shouting. So I can actually teach you how to recognize speech patterns, at least simple ones, without using any libraries. It's just some very simple signal analysis. If you want to know something like that, then let me know in the comments, because I might prioritize these things more now. But otherwise, eventually, I do want to see here other attacks like the special beam cannon or the Masenko or the solar flare. I know how to do many of those things, but yeah, and then other anime as well. Like I'm thinking about Rasengan and other things, a lot of things. I can do many things, but I just don't have so much time nowadays. So if you're interested in seeing how to do these and to see this future web page that can let you do any attacks in front of the webcam, comment below, make me do it, tell me it's important, that you want to see it, and you learn a lot of things with this. So this is knowledge way above things that you do in normal programming job. It's more like data science or machine learning or image processing, signal processing stuff. So if you're gonna have a CV with this kind of portfolio on it and you can explain what's happening there, you can get into many places. Like, yeah. So anyway, see you guys. Oh, forgot to do the traditional exit for this one.